Hello and welcome to Lecture 8. I am Alexandros Bakas, and together we will talk about operations on encrypted data, a modern family of cryptographic protocols. So, the first thing that we need to answer before we dive into details is why do we need to operate on encrypted data? The need for operating on encrypted data is derived from the following observations. First of all, once we store data on an untrusted cloud service provider, CSP, either unencrypted or encrypted with a key which is known to the CSP, privacy becomes an illusion. Moreover, once data are encrypted using traditional cryptography, they become useless in the sense that no matter what kind of modification or operation we want to do on our data, we first need to decrypt them, operate on them, and then re-encrypt them. Finally, and I hope that you will agree with me after the end of this lecture, it is an exciting topic. This lecture is structured as follows. We will talk mainly about two modern cryptographic techniques, that is symmetric searchable encryption and functional encryption. And for each one of these techniques, we will provide some definitions, some use cases, and finally, we will see how to build an SSE scheme or a functional encryption or multi-input functional encryption scheme. Finally, we will dig a bit deeper into a specific application of functional encryption, and that is how can we release statistics in a privacy-preserving way. Kicking off this lecture with searchable encryption, symmetric searchable encryption. Usually in an SSE scheme, we have two actors, Alice and Bob, where Bob here plays the role of a cloud service provider or a CSP. The scheme is initiated by Alice, who outputs a plaintext database and encrypts it locally to produce an encrypted database that consists of an encrypted index and a collection of ciphertexts. Now, as a next step, Alice outsources this encrypted database to the CSP, where it will be stored. Now, what is interesting with SSE is that at a later point, Alice can generate what we call a search token and send it to the CSP. Now, each search token is associated with a specific keyword, and the CSP, having access to the search token and the encrypted database, can actually retrieve all the files that contain that specific keyword and send back to Alice an encrypted result that she will decrypt locally. What's interesting to notice here is that the CSP can do so without learning neither the queried keyword nor the content of any of the encrypted files that were sent back to Alice as part of the encrypted result. Finally, since here we're talking about a dynamic scheme, we also assume that Alice can generate an update query that will naturally result to an updated encrypted database. Concerning the security of a searchable encryption scheme, usually what we do is we formalize it through what we call a simulation-based security game. Now, I understand that this may sound a bit weird to you, so I will try to give a very high-level explanation of how this works, but if you have any specific questions about that, please do not hesitate to reach me by email. In a simulation-based security game, we assume that there exists an adversary that monitors the real world, and by real world here, we mean the actual real algorithms of the SSE scheme. The adversary has control of the real world, which means it can provide the algorithms with inputs of their choice, record their output, and monitor the whole situation. Now, we assume that there exists a simulator that can simulate a view of the real world, in which we call an ideal world or a simulated world, in a way that is indistinguishable from the actual real world. Now, the catch here is that the simulator should be able to do so by getting as input only what is leaking from the real world, and we will talk about this specific leakage in the follow-up slides. We say that the SSE scheme is secure if and only if the adversary cannot distinguish between the real world and the simulated world. Again, I understand that this may sound a bit weird, so please do not hesitate to reach me by email if you have any specific questions on simulation-based security. Now, concerning the leakage, the thing is that to design more efficient SSE schemes, we allow the server to learn some well-defined leakage. So, for example, in the scenario that we saw before, during the setup phase, we assume that the CSP can learn the size of the database. During a search query, the CSP learns what we call the access pattern and the search pattern, where the access pattern is the outcome of a search query, and the search pattern is a vector that tells us whether and when is a search query repeated. Finally, during an update operation, the CSP can learn multiple information, such as the nature of the operation. That means whether the operation was about adding a new file or deleting an existing file, the unique identifier of the file that was updated, the size of the file that was updated, and so on and so forth. So, to minimize that leakage, we have two important properties that we'll see in the follow-up slides. These properties help us design more secure SS schemes with stronger privacy guarantees. So the first one is forward privacy, and it concerns the leakage during an addition operation. And the main goal of forward privacy is to make it impossible for the server to link newly added keywords to previous queries. So if we look at an example here, let's assume that at time 1, Alice adds a file f1 containing keyword w1 to her collection of ciphertexts. Then at time 2, Alice searches for w1, which means that Alice gets back file f1. And at time 3, Alice adds a new file f2 that also contains the keyword w1. So if the scheme is forward private, that means that the server should not learn that the update during time 3 is for the same keyword as for the search query that was performed at time 2. Now, along with forward privacy, we have its dual property, which we call backward privacy. And the main goal of backward privacy is that search queries should not reveal information about indexes of deleted files. So, if we look at a quick example again, let's assume that at time 1, Alice adds file f1 containing w1. Then at time 2, Alice adds a new file f2 also containing w1. At time 3, Alice deletes file f1. And at time 4, Alice searches for keyword w1. Now, since at time 3, Alice deleted file f1, she will only get back f2. However, the server should not learn what file was deleted at time 3. Notice here that it is impossible to hide from the server that a file was deleted, since the server stores all the files and it can easily know that after deletion operation it stores one file less than before. However, if the scheme is backward private, it should be impossible for the server to learn what file was deleted. Now, concerning backward privacy, we have different flavors of backward privacy, and in particular, we have 3 different flavors. So, we say that an SSE scheme is type 1 backward private if during a search operation the server learns the files that currently containing W and when they were stored. Then we say that it is type 2 backward private if on top of that the server learns also the timestamp of its update for its specific keyword. And finally, it's type 3 backward private if on top of the other 2 leakages it also learns which deletion cancels which operation. So what should you know after this lecture? So you should know what is a symmetric searchable encryption scheme. You should know how we formalize the security of an SSE scheme, that is the simulation-based security that we talked about before. It is very important to have understood what is forward and backward privacy and being able to express these notions in your own words. And finally, what are the different types of backward privacy. So thank you very much, and see you soon for more content.